Welcome friends. In this lecture we will solve one numerical on stator design, and the numerical is find the main dimensions of number of stator turns, size of conductor and number of stator slots of a 5 HP 3 phase 400 volt 50 Hz 1500 synchronous RPM squirrel cage induction motor with star delta starter having an efficiency of 83% and full load power factor of 0.84. Assume specific magnetic loading 0.46 Weber per meter square and the specific electric loading 22,000 ampere conductor per meter. Choose dimensions to give cheap design. Now if you read this example, then in this example along with the main dimensions it is asked to calculate number of stator turns, size of the stator conductor and the number of stator slots, and calculation of number of stator turns, that is TS, size of the stator conductor, that is AS, and number of stator slots, SS, is nothing but the stator design. It means in this example along with the main dimensions D and L we want to determine the stator design also. So by reading the example, first we will check the given data. HP is 5 HP, frequency is 50 Hz. Now here the speed is 1500 synchronous RPM. Synchronous RPM means directly NS is given. So the synchronous speed NS is equals to 1500 RPM. Now if the NS is 1500 and frequency is 50 Hz, then by the expression NS is equals to 120 F divided by P. The number of poles are 4. So therefore the given specifications of this machine are indicating the number of P for the induction motor is equals to 4. So it is a 4 pole machine and voltage is 400 volts. Efficiency is 83% and full load power factor is 0.84. Assume the specific magnetic loading 0.46 means the BAV is given 0.46 and the specific electric loading is 22,000. So here is the printing mistake. So instead of 25,000 here 22,000 is there. So the specific electric loading is 22,000. Now first we will calculate the main dimensions D and L. Now we will calculate the D and L from the output equation. D square L is equals to kVA divided by CO into NS, where the CO is output coefficient and its value is 1.11 kW BAV AC pi square into 10 to the power minus 3. And if the rating of the machine is given in the HP, the expression of the kVA is HP into 0.746 divided by efficiency into cos phi. So first, by using these two equations, we will calculate the kVA. The kVA is 5, that is HP, into 0.746 divided by efficiency 0.83 into power factor 0.84. So the kVA becomes 5.35, and the output coefficient CO. Now in the expression of the output coefficient, kW is there, but if you read the example, the kW is not given. So let me assume in this example the full pitch winding, and for the full pitch winding the kW is 0.955. So with this assumption, if we calculate the CO, then 1.11 into 0.955 is kW, into 0.46 is BAV, into 22,000 is AC, into pi square into 10 to the power minus 3, and if you calculate this, you will get 105.88. As the synchronous speed is given 1500 rpm, so if you calculate in the rps, then it will be 1500 by 60, so you will get 25 rps. So just we will put these values in the expression of the d square L, then the d square L becomes 5.35, that is the kVA, divided by 105.88, that is CO, and 25, that is NS. So you will get, after calculation, this 0.00202. Now it is asked in this example, choose the design which gives the cheap design. So for the cheap design, as we know that the ratio L by tau is 1.5, and the value of the tau is pi d divided by p. So the expression for the L is 1.5 into pi d divided by p. As I already told that this is the 4-wave machine, so you can write the L is equals to pi d divided by 4, and this expression becomes 1.17 into d. Now let me insert this value of the L in the equation 1. This is the equation 1. So if you insert here the L, then this value becomes 1.17 d cube is equals to 0.00207. And from this equation, if we calculate the value of the d, then the d is equals to 0.119. And now this value of the d we will put in the equation number 2. So the L is equals to 1.17 into d, and the d value is 0.119. So if you calculate this, you will get the L value as 0.14 meter. And if we check these two values at the peripheral speed, then the V is equals to pi d ns, where the d is 0.119, and if you calculate this, you will get the 9.42 meter per second, which is less than 30 meter per second. So the calculated value of the d and L are accepted, and our final answer for the main dimension is d is equals to 0.119 and L is equals to 0.14 meter. And as we know that if the length is 140 millimeter, 0.14 meter means 140 millimeter, we requires one ventilating ducts, as the ventilating ducts is required for every 125 millimeter length. Now after finding the main dimension, let me find one next quantity, that is the TS, that is the stator turns per phase. And this stator turns per phase is calculated from the EMF equation. As we know that from the EMF equation, the TS is equals to ES divided by 4.44 into kW into F into 5. Now in this equation, the kW is given, that is, or we have already assumed this kW is 0.955, and the ES, this is the EMF in the stator per phase, because we are finding the turns per phase, so it is EMF per phase. And in this example, the voltage is given 400 volt. So the given voltage is 400 volt, and it is said there the machine is started with the star delta starter. If the star delta starter is used, it means the machine is running under the delta connection, and for the delta the phase value is equals to the line value. So that means the given 400 volt is definitely the line value of the voltage, but because of the machine is running under the delta connection, that phase is equals to line. So the EMF per phase we can take directly as the 400 volt here. So only unknown parameter in the equation of the TS is phi, and this phi is calculated from this equation. Phi is equals to BAV into pi del divided by P. So first we will calculate the phi by using this equation, and then we will put in the equation of the TS. So we will get the value of the number of turns per phase. So the phi is equals to 0.46, that is BAV, into pi into D calculated value is 0.119, into L we have calculated the L as 0.14, divided by P. P is the number of poles, that is 4, and if you calculate this you will get 6.0695 into 10 to the power minus 3. And now if you put this value of the phi in the equation of the TS, then the TS becomes 400, that is ES, divided by 4.44 into 0.955, that is kW, into 50, that is frequency, into 6.0695 into 10 to the power minus 3, which is the value of the phi. So if you calculate this, you will get the number of stator turns are 311. As the number of turns are usually even in numbers, so we are just approximately writing that is equals to 312. Now the next parameter is the size of conductor. Size of conductor is nothing but the AS, and this AS is the ratio of IS to the del S. So IS is the stator current divided by del S is the current density. As we know that the IS is kVA into 1000 divided by 3 into ES. So just we will put the values in this equation. We will get, as we know that the kVA value is 5.35 into 1000 divided by 3 into ES value is 400, we will get the current IS as 4.458 ampere. And for the current density, we have already discussed in the lecture that the usual value of the current density is from 3 to 5 ampere per millimeter square, and normally it is selected as 4. So we have taken here the current density 4. So therefore if we take this value of the current density and the stator current in this equation of the AS, then the size of conductor AS can be written as 4.458, that is the value of the IS, and divided by 4, that is the value of del S. So we will get 1.1146 millimeter square. And the last quantity asked, that is calculate the number of stator slots. As I have told while discussing in the previous lecture, the number of stator slots are normally chosen as the 3 per pole per phase. So the number of stator slots are 3 per pole per phase. As in this example, number of poles are 4 and number of phases are 3, just it can be written as SS is equals to 3 into 4 into 3. Once again, just I will describe how this equation works. 3 per pole per phase means for one pole and one phase 3 slots are required. It means for 4 poles the number of slots are 3 into 4, and for 3 phases we have to multiply by 3. So the total number of stator slots are 3 into 4.3, and if you calculate this you will get the 36 answer. So these are the all quantities which are asked in this example. Now similar type of 2 examples I have asked in the exercise. So I request all of you watch this video carefully and solve this exercise at home and submit me. Thanks for watching.